and we continue with our interesting presentations about matching geology and physical systems with modeling. So now we begin the session with Henk Kooi, that presenting a study case of the Netherlands. Thank you very much.
Thank you. So welcome back at this modeling session. My name indeed is Henk Kooi. The first author, the second name you may have seen somewhere on this conference round. I will talk about a very typical Dutch problem. I doubt it will be a problem, an issue elsewhere in the world. It's about nitty-gritty water management, dynamic water table conditions in very small range. That's relevant in this country. I will first introduce that issue, the background I find particularly relevant before I get to the modeling aspect. So we have a long history of living with soft soils in the Netherlands, as you probably know by now. This shows it again, like a cross section from Utrecht in the east to Rotterdam in the west, on the Holocene delta. You see a cross-sectional profile. The black line, the black line here is, it's very hard to, the black line is the base of the Holocene. So below it, the yellow colors are mainly Pleistocene sands. Stiff sands are not really concerning for land subsidence. On top of that, you see the greens and the brown reddish colors. The green mainly clay and the brown reddish peat. In blue, the sea level roughly, and as you know, the last 1,000 years we worked our way down from above sea level in that area by peat oxidation, by excavation of peat, drainage issues, and also soft soil compaction. That's what I'll talk about. Compaction mainly is still very prominent in urban areas mainly. Which you can also see in the graph, Gouda, Rotterdam. You see the gray stuff on top in the profile. That's anthropogenic material that people put there to build their cities and to live on and to raise the land. But of course it loads the subsurface, it drives compaction. And that's still an issue. If we look at the INSAR map of the Netherlands shown earlier, for this part of the country, you see the red and the yellowish subsidence, predominantly subsidence. That's all urban built-up area in the INSAR. Roads, infrastructures, buildings. So that's mainly loading areas. So it's not representative of other background processes. So volume loss by compaction, subsidence. The basic principles like Terzaghis effective stress concept is relevant for compaction. So you can drive subsidence by increasing effective stress in two ways, by either increasing the total stress in the subsurface. That's mainly what you do by surface loading, putting loads on the surface, but you can also lower the pore pressure by drainage or lowering groundwater. In other parts of the world, major pumping. For us, it's lowering groundwater levels by drainage, controlling drainage. Very subtle differences. Very basic principles. In the Netherlands, of course, we have a long time of experience and our own software for predicting and modeling settlement due to loads on these soft soils. It's a huge area. And the left graph shows you, or the right, the graphs like surcharges of sand put on top of these soft soils to consolidate them. And on the left you see then like an original condition without the surcharge, and here with the surcharge. And that of course increases the total stress and thereby effective stress, starting a new cycle of compaction. Well, we do a lot of modeling engineering. It's in this university, everyone or a lot of large students are very familiar with this, and we're using the software like building subsurface strata with properties and loading. This is let's say, loading steps on a log time scale. This is 30 years typically that is calculated in predictive settlement modeling. And then you predict like settlement history over time. And you see here the stepwise, here the settlement. Of course, then when you do that, you put, you count the subsidence, or the settlement is taken into account by building up the soil, by adding loads. You want to end up at a certain level, but you can't wait 30 years before you can live there. So this is done for a couple of years or so of construction, and then the total surcharge is settled to a certain level, maybe here after a year or so. And then, of course, you have to put in the pavement and the road, etc. And then you start live there. But the subsidence and the settlement continues, residual settlement. So, residual settlement for decades. It's not huge. I mean, maybe centimeters, millimeters per year. But it's a long time and perpetuating process, residual settlement. And this is what we need to take into account and we model as creep. Right? Well, these millimeters per year or centimeters or millimeters, that is very, very relevant in the Netherlands. An example here from Gouda. I mean, when you're in a situation like this after a while, then you need to do something, right? On the left, this is the land level next to the canal. So, and then another cycle of action needs to be taken, but at some point, the water management, etc., they have not many options anymore because they cannot really lower the water level in the canals for many reasons I'll not explain. So they need to think, they need to do something about it, right? And this is Gouda. It shows also a typical profile here of peat up to about 10 meters or 8 meters below sea level here. And you see the historic anthropogenic levels of many, many meters of materials that people over the century have put on top to try to keep a little bit, to keep a bit of elevation in the system. But it loads again and again new cycles. Okay. So what are the options? Well, we cannot deal with everything, but one thing that's important that people do is try at least to keep the pore pressures as high as possible in the system, because lowering pore pressures is also increasing effective stress. So water managements are looking for all options to keep water pressures relatively high. And of course, then you can try to keep the water levels in the surface water system as high as possible. And at the same time, you want to lower it with climate change, etc. It's a dilemma. Second is very, very important, not just in the Netherlands, prevent unwanted drainage by leaky sewage systems, because if once they become leaky and they drain the groundwater, it will lower the groundwater level. You probably don't notice for a while, and it induces subsidence. You won't get it back, right? And the third one is like a mitigation activity that's done in the Netherlands. That's using infiltration drains. So in summertime, when you have the dry period and the groundwater levels lowers, like you have not just drains to get during wet periods the groundwater away, drain it away, but to get it infiltrate groundwater from surface water into the ground during low groundwater level, to keep it relatively high up, to prevent it from declining. That's shown here on the right, a graph of groundwater level measurements. This is in Amsterdam, by the way. My pointer is not doing the right thing. Yeah, here it is. You see here groundwater level varying over the many years, up and down, about 1 meter somewhere, and they put in a system with infiltration drainage, and then that stabilizes the dynamics of the groundwater movements, with the idea that it might help to mitigate a little bit the subsidence. But is it? That's another question, a practical question. I mean, it's an investment. Is it worthwhile? Should we do this? Really? Does it help? Well, who can tell? Well, we don't know, but at least we give it a try in many different ways to answer this question. We didn't have the tools to actually model it, because that's one approach, try to get an idea with modeling. But this issue, does it help? Of course, we have some elements for a theory. So we built, let's say, a 1D vertical column model to simulate the response to groundwater level variations. So this is like the model domain is just 1D, let's say the Holocene deposits, like in this gray, and you can put all kind of stuff in there, clay, peat, what have you. On top of that, the yellow is not directly a part of the model calculation part, but it's to drive the boundary conditions at the top of the clays. And this is, let's say, the urban level, sands or whatever that people have put on top, in which the groundwater is moving up and down seasonally. Right here, the dynamic water table. But we want to calculate what's going on in here in terms of processes with clay and peat. So of course we have like we need the Darcy type groundwater flow exchange in there, and we need consolidation and the coupled to the deformation and swelling and creeping. It will go up and down, right, in various ways. And the dynamic water table drives the boundary condition here by the hydrostatic, the hydraulic head varies, of course, at the top of this gray part of the model. Specified head, which is variable in time, specify for measurements or general. And of course, then the weight of this cover changes as well with the groundwater table, which loads and unloads, let's say, the peat and the clay in here. That can be put into the equations and model. And we just see what happens and what we get. That's the basic model, and for the deformation model, we use the Dutch, let's say, NL soft soil engineering compression model, which is illustrated here. It takes a bit of time to explain. I won't go into details, but this is like in the diagram, the log of effective stress on the vertical, and on the horizontal and on the vertical, you have the strain, right? So you may recognize here an elastic component, elastic state line here with increasing effective stress, elastic deformation part. And then there is like an old-fashioned Terzaghi model, this would be the virgin compression line. In the Dutch model, we need creep. This is not a single state line. All these lines here are, in the Dutch model, lines of equivalent creep rate. They have the same rate, and the rate decreases. This rate line here corresponds to a very slow creep rate. This reference line to a certain other higher creep rate. And when you move above this line, the creep rate increases dramatically. So it is a generalization of the more conventional elastoplastic model. That's what we use in the Netherlands, with various parameters in there. So that's used in engineering. We implement it in this model. I show you a couple of experiments with the model, inspired after Gouda. Okay, inspired after Gouda with peat and clay in here, parameterized, etc. And we're going to vary the groundwater level in there. I'll show you a couple of scenarios. A reference scenario where we have the groundwater moving up and down 1 meter in this anthropogenic level range. Let's just modify that and include one dry year when we have a 0.5 meter extra drought impact on the groundwater level and see how that affects the outcome. Or we can do the damping, like for the infiltration systems, impose it and compare it to the reference. What difference does it make? Or raising the groundwater level if there is any opportunity to do that. Right? I'll show you the outcomes. For the reference, on the left you see a starting condition maybe long after the previous loading cycle, so there's a low residual rate of creep. The black line is creep. And you see also the elastic deformation on top of the creep. But the black line is the more important one. That's the irreversible part of the strain. On the right you see a reference case where you start, let's say, with a condition that's where the loading was relatively recent and with a high rate of subsidence. You see, by the way, here that the creep rate it varies in time. The black line is a bit wavy. That's because of the response in the creep to the changes in effective stress, or the dynamic changes in stress, a bit wiggly. Well, just the case here, you see some impact on the subsidence here. The black line is dipping here during the drought year, dry year below the reference one. That's the gray one here. So a couple of millimeters difference in this model for one dry year of irreversible compaction. This shows a similar for the damping. Well, you tell me, do you see much difference? Not a lot, right? A small percentage on a couple of millimeters on the left. On the right, you see raising groundwater level. That's a major impact. If it's possible to do that, you'll get a response like this. That is just like an exploratory tool. So we did this to try to answer that question, the issue, practical issue for water management. So we have a novel framework to do it. But then, yeah, how good is this? Do we have the answer now? Of course not. I mean, this is just what the model framework gives. And we need to assess if this makes sense in the real world. It's all about this compression model. Is the compression model valid for this range of stresses and loading? And that's very doubtful, but it's the best we have at present. So we're in a process of trying to test this framework for the small load changes and the creep impacts to see if this model makes sense in various ways. That would be several other talks to fill, but I'll just mention that that's ongoing work, and I'll leave it at that. Okay.
So we have time for 2 questions. Questions? No questions of the audience?
So at the end, it is working, this measure about taking the pore pressure or trying to keep the pore pressure in the limit of secondary compression, or in this sensitive balance. It is working, this
it's
measure.
It's a very sensitive balance. And we know from monitoring that these systems, like they implement, they do manage to affect the groundwater dynamics. But the question for us is, does it make a difference on the subsidence? And there we don't have a clear answer. Our tests for the model in the lab, in the field, we have not been able to get definitive results on tests. So it's totally unclear. It's totally in the noise level of measurements like what we get from field tests. In the lab, we have the impression that our compression model is not, it's not designed, it's for engineering purposes, for large loading. It's been tested and evaluated. We use it out of the range for which it was originally developed, because we don't have anything better. And our lab tests, they do provide an indication that we may be way off, and that the effect of these small load changes is much larger than predicted in this model, but that's still ongoing work.
One last small question, I think.
Thanks a lot, Henk. Were you expecting the results that you got? Because especially the example where you limit the amplitude, virtually not affecting the creep, was that something you expected, or was it also?
To some extent, yes. If you have a little bit of feeling for this creep model, then you know that it's like the creep, as you saw the wavy curve. Is the subsidence is like the creep integrated over time. It's just the rate subtly increasing during low groundwater levels and then decreasing a bit in winter. So that gives you only every year a subtle deviation relative to if you don't have the cycle.
Okay,
So, yeah,
let us thank the speaker again.